Hello, welcome back to the final lesson of 8.5 Applications of Matrices. And you know that matrices have a ton of applications, right? So we're going to discover maybe about 3 more today. And I'm sure you're aware that we've done some encryption, so that was really fun, decoding and encoding, right? Okay, so let's finish up, okay? These 2 applications are really cool, actually 3 applications, okay? Now, applications of matrices and determinants. All right, so I told you determinants are like special numbers, right? So they actually have a lot of applications. You can even find, part 1, area of a triangle using matrices. Oh my gosh. If you know 3 sides, 3 points on a triangle, then you can even find the matrix area of them using matrices. So this is kind of a cool trick, right? Yeah, I think sometimes this is going to be kind of powerful for you. Given a triangle with 3 vertices, x1, y1, x2, y2, x3, y3, the area of a triangle can be found by using this. So there's a special formula here. Area equals plus or negative, right? Because the determinant could be positive or negative value, but as we know, an area of anything has to stay positive, okay? So area of a triangle is plus or negative half of this. Now, if you're really curious, please look into look into the actual proof of this beautiful formula. It works wonderfully, okay? So obviously these are the points, and you have a 1, the third column to be all ones. And you know, this half, it's kind of like half base times height, don't you think? So maybe this is somehow related to that, okay? All right, we don't have time for that right now, but I know that if you're wondering, please look into the proof, okay? So let's try one and make sure that it works, okay? Of course, you're allowed to use a calculator, but we can use a 3x3 method, right? So let's try that. So find the area of this triangle, and we're given these 3 vertices. This is from number 8 from your textbook. And so let's try, okay? Find the area of the vertices. So area of a triangle using determinants of a matrix is going to be plus or negative half. And you have your coordinates, x1, x2, x3, y1, y2, y3, and a column of 1s. All right. So how do we do that? Let's actually just use some fill in the blanks, right? So let's actually fill in all the vertices that we know. So plus or negative half. And let's plug in 0, negative 2, negative 1, 4, 3, 5. Line it up nicely so you can actually calculate easily, okay? So 0, negative 2, negative 1, 4, 3, 5. And we're going to find the area of this magically, okay? So what do we do when we're finding the determinant? We actually write the first 2 columns correct. So 0, negative 1, 3. Negative 2, 4, 5. And let's calculate, okay? So plus or negative half. If you want, you can use a calculator, but I'll just use my hands, okay? I think sometimes it's easier to actually calculate in your head than punching these into the calculator. So I'm going to punch it in. So let's do this side first, right? These diagonals here. 0, 4, 1 is 0, plus negative 2 times 1 times 3 is going to be negative 6, plus negative 1, a positive 1, negative 1, 5 is going to give you negative 5. That's this diagonal, right? That's this diagonal. Let's do the next diagonal, which goes this way, right? 1, 4, 3, that's going to give me 12, plus 0, 1, 5. When I multiply them, it gives me 0. Negative 2, negative 1, 1. That means it's going to give me positive 2. So what do I get here? I get negative 11 minus, this is a 14, so minus 14. So I got half of plus or negative half of negative 25. So the area of this triangle is going to be negative 25 or positive 25 over 2, or you can say 12.5. And that's the area of this triangle. Don't you like this method? I think this is like so powerful because you're not thinking about, oh, where is the base? Where is the height, right? With these 3 vertices. I mean, you can sketch it out, I guess. 0, negative 2, you know, you can do all that. But I just feel like this is kind of a cool method. I have a feeling that you guys really enjoy it, but you're too scared to admit it, okay? All right, let's go ahead and do part 2, another application of matrices, which are collinear points. Did you know, just with matrix determinants, we can actually see if points are collinear. Ooh. Now, collinearity, I don't know if that's really a word. Collinearity has a lot of applications in itself. If points are collinear, you know that it does not form a plane. Therefore, it's a straight line, right? So there's a lot of application to this if you think deeper about it. So let's do collinear points, okay? Now, here's how you, now think about this, okay? It kind of has relationship with this area formula if you think about it. how would you know if the three vertices that you're given, how would you know if the three vertices that you're given even form an area or not? Now, what if this guy here gave you a 0? Does that mean that these 3 points, what would that mean about these 3 points, right? Think about that deeper, okay? All right, so now that you've had something to think about it, collinear points. Now, it's kind of same, right? You're using determinant, but given these 3 coordinates, if it equals 0, right? If it equals 0, what does that mean? It means it has no area, right? Because there is no surface in order for me to actually have area, right? Makes great sense, doesn't it? So I'm sure a lot of you guys had figured that out before I even told you. So let's actually try one, okay? So that's it. So if your determinant equals 0, given 3 points, then you know it's collinear. Because if it's not 0, then you know that it's got an area, okay? So that means it's in a plane, right? Okay, so let's try that, okay? Let's try with this guy here. We're going to ask you this question. Hey, are these given points collinear? Are they? Well, let's check, okay? So what are we going to do? We're going to see if the determinant is 0 of these 3 coordinates. -3, -5, and 1, 1, 1. We'll just fill that in. 6, 1, 10, 2. We're going to now calculate the determinant using this method. I'm sure no one's using minors and cofactor methods for these, right? I wouldn't suggest it, okay? So I'm going to do this diagonal first. So -3, -50, because I'm just multiplying. -3 times 1 times 1, -5 times 1 times 10, 1 times 6 times 12, which is 12. I'm sorry, I already did the calculation, right? Subtracted by the product of these diagonals here. 1, 1, 10 is 10. -3 times 1 times 2 is -6. -5 times 6 times 1 is -30, okay? And do I get 0? So remember, our question is, are they collinear? So we should put question marks, right? Are they 0? So let's check it out, okay? This is going to be what? -53, right? -53, +12, so that's going to be -41, right? -41. Minus 4 minus 30, right? That's 4 minus 30, which is going to be -24. So does that equal 0? Our conclusion is it does not equal 0 because this is -26, right? So when we do that, we get -15. And we're like, wait, that's not equal to 0. Therefore, our conclusion is, therefore, the points are not collinear. So we can assume from your old geometry days that these points actually will create a plane, okay? All right, watch the next video for more applications on this formula here, just the collinearity, okay? 2 more examples coming up soon. Bye.